Welcome back. Let's now finish up by looking at a side-by-side comparison of the runtime complexity of lists and linked lists. And here, there's a few minor variations, but let's assume it's a doubly linked list that's circular, and the sentinel or not the sentinel doesn't really matter. But let's assume it's a doubly linked list because that's sort of the more general type. So let me just remind you that with a traditional list, we have the following functions that we want to operate on: insert, append, delete, find, access. Insert means insert something into the middle of the list. Append means you append it to the very end of the list. Delete, pull an element out. Find says search for this element, assuming unsorted. And access says give me the kth element. Okay, so insert is big O of n. N is the length of the list, obviously, in all these cases. Why is it big O of n? Well, because if I insert, for example, the first element of the list, everybody's got to move over. So in the worst case scenario, I've got to move a lot of elements. Append is typically big O of n because if there's no room in the list and I want to append at the end of the list, sure, nobody has to move. Everybody stays in the same place. But if there's no memory, I've got to move everybody from where they are to a new place in memory and then add myself. And the only reason we put this exception here is because Python is pretty clever, and when they allocate memory for a list, they typically allocate more than it needs, and that way you can append to the end of the list without incurring the cost. But worst case scenario is it's going to be big O of n. Deletion has the same problem as insertion. If I pull something out from the front of the list, everybody's got to slide back. Now, obviously, if I delete from the end of the list, that's fine. It leaves an empty spot. But the worst case scenario is everybody has to move to fill in the gap. Find is we have to search. There's nothing sorted here. You got to start at the beginning, go to the end, search every element. Worst case scenario is it's the last item in the list or it's not in the list, big O of n. But the big win for lists is random access, which I can get to the kth element without having to go between 0 and k minus 1. And the reason, of course, is that every element of the list is stored with a fixed amount of memory. And if I want to get to the kth element, I simply have to take one big step of k times that size of memory, and I'm at the kth element of the list. So big win for random access. Okay, now for linked lists, which I will say instead of saying doubly linked list every time, but we'll be using double circular linked list. Insert is big O of 1. And the reason why it's big O of 1 is once I tell you where you want to insert, you simply have to rewire either 4 links or 2 links if it's singly linked list. And that's, of course, because the nodes are connected in this loose affiliation. There's no notion of being in the 5th position. You are simply in the 5th position by virtue of having 4 nodes before you. So if I insert something in there, you are now in the 6th position. You didn't have to move, right? It didn't burden you in any way. So insert and append are big O of 1. Append in particular for a circular linked list is I can get to the last element of the list in O of 1, and then it's just an insert operation. So that's also big O of 1. Deletion is big O of 1. Once I tell you what nodes you want to delete, you pull it out by simply rewiring, and it doesn't matter how many nodes are in the list. Now, find, just like a list, is big O of n. These lists aren't sorted. You got to start in the first element, and you got to get through the whole list. It doesn't help, doesn't hurt. Okay. Now, here's where we're going to take the hit, of course, which is that random access is big O of n. And by the way, why am I saying big O of n? How do I know which element you're going to index into? So again, this is the worst case scenario. If you want to get to, say, the midway point, which in a circular list is the worst case scenario, because either you can go forward or you can go backwards, that is n over 2 iterations, and n over 2 iterations is big O of n. So worst case scenario is there's no way of getting to the ith element of the list without following these pointers, and that takes time proportional to the length of the list. So you are hired as a software engineer and you have to make a decision. Do I implement a list or a linked list? I don't know. It depends. So what does it depend on? Well, if random access is going to be the main operation you do, then there's no debate. If your data is largely static and you're just shoving a bunch of stuff in there, and since append maybe is reasonably smart if it's implemented in the right programming language, lists are the way to go. Super easy to implement, no work to be done. Random access is your main operation, go. If, on the other hand, your list is highly dynamic, you're constantly adding and removing and appending, and that is now going to start to get a little costly up here, so maybe you want to think about this linked list. On the other hand, if random access is also really important, now you have a dilemma, right? Do you do this or do you do this? Because this is super cheap here, yeah, but this is going to cost you, and so now you have to make a decision. And what other factors are there? Well, complexity of implementation. Lists are really nice. They're built into the programming language, whereas these you actually have to build and debug and write all the classes. And so you have to make decisions. And those decisions are not just which data structure do I like better. Those decisions are, what is the nature of my problem? What is the nature of my data? What is the nature of the algorithms that will operate on the data? And only by knowing how the various operations you want how efficient they will be, can you make an informed decision. Okay? All right, so that was our second data structure, our singly and doubly linked lists. And now what we're going to do in the next series of lectures is introduce some more data structures, and it's going to follow the same theme. I'm going to give you some intuition, we're going to write the classes, we're going to write some algorithms, and we're going to do the runtime complexity. And the hope is that these data structures will sort of build out your understanding of how to represent data and how to operate on that data. All right, that's it for this lecture, and then when we pick it up, we'll start with a new data structure.